During manufacturing, certain materials may undergo processes that alter their grain structure and enhance their mechanical properties. Heat treatment processes are used to change the physical properties of metals, enabling them to be utilized across a wide range of industries. These heat treatments vary based on the type of metal and the specific mechanical properties required for the part's function. Depending on the desired characteristics, we can choose from various processes, including annealing, normalizing, tempering, quenching, and others. In this video, we will take a detailed look at the normalizing process. By the end of this video, you should have a better understanding of this important method. Welcome to the channel. What is normalizing? Normalizing is a heat treatment process that involves heating the material to a temperature above its upper critical temperature. The material is then soaked at this temperature for a specified duration until transformation occurs. After soaking, the heated material is removed from the furnace and cooled to room temperature in ambient air. The upper critical temperature, A3 or ACM, as represented in the iron-carbon diagram, defines the temperature at which steel becomes 100% austenite during heating. This temperature varies by composition, ranging from 910 degrees Celsius for pure iron to 727 degrees Celsius at the 0.77% carbon eutectard point. For hyper-eutectored steels, this upper limit is represented by the ACM line, indicating the temperature where cementite fully dissolves into austenite. This line slopes from 1150 degrees Celsius at 2.4% carbon to 727 degrees Celsius at 0.77%. When a metal is normalized, austenitic grain boundaries begin to emerge because the metal is heated to a temperature roughly equivalent to its hardening temperature. After cooling, the material forms ferritic grains, which create a finely grained structure with predictable physical, corrosion, and machinability responses. Normalizing is typically performed after metal fabrication processes, which can alter the material's properties. Examples of such processes include stamping, forging, hot rolling, welding, and casting, all of which may induce significant thermal and mechanical stresses in the material. The purpose of normalizing is to relieve the internal stresses resulting from heat treatment, welding, casting, forging, forming, or machining. Normalizing allows the grain structure to realign into a more uniform arrangement, returning the metal close to its original properties. By facilitating recrystallization and transformation of the distorted or brittle microstructure, the material achieves a more refined and balanced grain structure, enhancing its strength and ductility. Key parameters to consider during the normalizing process include heating temperature and soaking time, which depend on the type of material, its initial hardness condition, and the desired degree of change in its properties. Stages of normalizing. The normalizing process consists of 3 stages: recovery, recrystallization, and grain growth. Recovery stage. In this stage, the material is heated to a temperature that allows its existing non-uniform grain structure to undergo refinement. This temperature typically ranges between 780 degrees Celsius and 950 degrees Celsius for most steels. The goal of this stage is to relieve internal stresses caused by cold work or casting. As the material is heated, thermal energy enables the atoms in the crystal lattice to move freely, allowing the deformation of microscopic defects and relieving internal stresses and potential fracture initiation points. The recrystallization stage. The recrystallization stage is the most critical phase of the normalizing process, occurring after recovery. During this phase, the microstructure undergoes significant changes, including grain boundary dissolution and atomic diffusion. This stage takes place between 780 degrees Celsius and 950 degrees Celsius, depending on the carbon content of the steel. The metal is held at this temperature for a duration known as soaking. The aim of this stage is to create new grains that are free of existing pressures. As the material reaches the recrystallization temperature, new and smaller grains form within the existing microstructure. These new grains progressively consume the older grain structure, resulting in a more uniform austenitic matrix. The recrystallization process enhances the metal's ductility and hardness. Grain growth stage. During the grain growth stage, the material is cooled from the recrystallization temperature to room temperature in air. During recrystallization, the coarse old structure dissolves and forms smaller new austenitic grains. As the material cools below the transformation temperature, the uniform, coarse austenitic grains produced during soaking or recrystallization transform into new, fine-grained ferrite and pearlite. The faster cooling rate, compared to annealing, limits the time available for grain growth. This rapid cooling helps break down the coarse carbide network and reduces chemical segregation, resulting in a more uniform structure. It renormalizes the coarse-grained structure often caused by previous hot working or casting into a finer, more uniform structure. The final grain structure is typically smaller and more uniform than what existed before the process, which enhances mechanical properties such as toughness, ductility, and machinability. The final microstructure achieved during the grain growth stage depends on several factors, including the type of material, its initial condition, stable temperature, and the hold or dwell period. Microstructure of normalized steel. The thickness of carbon steel can significantly affect the cooling rate and, consequently, the resulting microstructures. Thicker pieces cool more slowly and become more ductile after normalizing than thinner pieces. After normalizing, sections of steel containing 0.8% carbon typically feature pearlite, while areas with low carbon exhibit ferrite. The redistribution of carbon atoms occurs between ferrite, 0.022% by weight, and cementite, 6.67% by weight, through atomic diffusion. The amount of pearlite in normalized steel is greater than that in annealed steel with the same carbon content. This results from a shift in the eutectored composition to a lower value and the subsequent formation of cementite. Advantages of normalizing. 1. Enhances mechanical properties by refining the microstructure, which increases strength, toughness, and ductility. 2. Reduces residual internal stresses induced by prior manufacturing processes, minimizing the risk of distortion, cracking, or warping during or after machining. 3. Produces a uniform, fine-grained microstructure, resulting in greater material consistency and reduced anisotropy. Disadvantages of normalizing. 1. Air cooling is slower than quenching, which can limit production rates and increase cycle time, particularly in high-volume manufacturing environments. 2. May cause minor dimensional changes or warping, especially in components with non-uniform cross-sections or complex geometries, due to differential thermal expansion and cooling rates. 3. Primarily applicable to ferrous alloys such as carbon steels, alloy steels, and cast iron. If you found this information helpful, please like this video, share it with your friends, and subscribe and turn on the notification bell for more engineering and metallurgical content. Thank you for watching, and see you in the next video.